Hello, I'm Neil Robertson doing exam 2 for transport 2. In this problem we have a wetted tube on the inside where we have gas flowing up, evaporating the liquid flowing down. And we're going to be looking at the mass transfer evaporation. And to do that, we're first going to use dimensional analysis to simplify the scenario using the Buckingham Pi method. For this method, we have to decide on every variable that plays an effect in this problem. That would be the mass transfer coefficient, the velocity of the liquid, the density of the liquid, the viscosity of the liquid, the mass diffusivity constant, and a dimension of length. Now, once we figure out those variables, we have to look at the units used, and there's 3 units of mass, time, and length. So we're going to be using kilograms, meters, and seconds. And then you're going to take each one of these variables and assign them values in the matrix depending on what their units are. For our mass transfer coefficient, we have meters per second. So in this example, 0 for kilograms, meters on top for 1, and seconds on bottom for -1. So velocity, meters per seconds, same thing, 0, 1, -1. Density is kilograms, 1 per meters cubed, -3, 0 for seconds. Our viscosity is kilograms per meters per second. So kilograms, 1, meters -1, seconds -1. Our mass diffusivity constant is meters squared per second, so 0, 2, -1. And our length dimension is just meters. So we're going to have to figure out how many dimensionless groups we're going to be needing for this method. To determine that, we'll be using I for independent dimensionless groups, bigger, equals our n, or number of columns minus the rank. Yes. All right, I'm going to go over the determination of rank from the dimensional analysis. We're going to just use NumPy to accomplish that. Okay, so the only thing we have to do is input our matrix and then use a function of the NumPy import to give us the rank back. So we're going to put the matrix into an array, and then I just copied it so we don't have to go through writing all 3 rows, 6 columns of it. And then after you put in the matrix into the array, you're just going to use the NumPy len algebra, and then use the matrix rank right there. Oh, almost forgot. We have to give our array matrix a name. We'll just call it matrix MTX, MATX for short. Just put that into our rank line, run the program. You get our rank is 3. We have 6 columns and rank equals 3. So our independent would equal 3 as well. So we have to have 3 what we'll call pi groups for this dimensionless, for these dimensionless groups. So we'll just go pi 1. Well, first we need to determine how our groups are going to be made. So for this, you have to have at least 3 core groups. And these core groups have mainly one rule, that between the 3 of them, you have to have kilograms, meters, and seconds all show up. So you can't use 3 things that don't have kilograms or mass show up in their units. So for this, you can take any other group. I'm going to use the mass, diffusivity constant, density, and our length dimension, which gives us kilograms, meters, and seconds, leaving us our 3 other groups we'll use once for each pi group. So for pi 1, we'll use the mass transfer constant, and it'll be, so first I'm going to put our 3 core groups. Those we don't know what power they're raised to for units to cancel out, so that we get 0 since they're dimensionless groups. So we'll assign A, B, and C to our variables of our core group, and we'll be doing this again with different letters, and then our K, and then we just add our mass transfer constant, which is just raised to the 1 power to tell you those units have to be there. And then the rest make up the canceling out for the dimensionless group. Do this again, move on to the next 3 letters, D, E, and F, assign them for the exponents, and then use the next one, velocity. And then for our last group, this might not be enough space. Fit it. No. Same thing, moving on to G, H, and I, and then our viscosity. Now we're going to look at each of the units of these variables and cancel them out, going from 3 different equations using 1 for mass, 1 for length, and 1 for time. So for our pi 1 group, we have our units, meters squared per second to A, and then you have kilograms per meter cubed, and meters to C. And then we have our group that has to be in there to the 1 power, our mass transfer coefficient in meters per second. So for kilograms, we have 0 for A, 1 for B, 0 for C, and 0 on the non-core group. And this always equals 0. So we know B equals 0. For our meters, we have 2A, and then we have -3 for B, so -3B, and then we have 1 for C, so plus C, and then plus 1 for the non-core group equals 0. Now we can't solve that one quite yet, even though we have B. So we're going to look at the time, or seconds, which is -A, nothing for B, and then nothing for C, -1 equals 0. So we know that, make sure I did that right. So we know that for seconds, for the A group, we have negative A minus 1, which goes to A equaling plus 1. A equals negative 1. So using B equals 0 and A is negative 1, we get negative 2 minus 0 plus C plus 1. So minus 2 minus 0 plus C plus 1 equals 0, making C equal double check that, so you minus 2 minus that would just C equals 1. So minus 2 minus 0 plus 1 equals 0, checks out. Almost made a mistake there. So that gives you, go back looking at the groups, correlating back to here, using those sets, you get pi 1 is equal to you get this, having C equal 1, A equals minus 1, and the non-core group equal 1. So you have the length dimension times the mass transfer coefficient divided by your mass diffusivity constant, which is also the same as the Sherwood number, which we'll need. All right, I'm gonna move that so we have our space. So then our pi 2 group, and we're going to do the same thing, same variables. We have our meters squared per second for mass diffusivity constant, our density, kilograms per meter cubed. Almost forgot to put in there exponents. Meters. And our velocity, which is meters per second. We're going to do the same thing for this as the last. So we got kilograms, meters, second. So again, we have D equals 0, E having to equal 0, starting out with kilograms in the non-core group. F is 0, this is 0. Get the same setup since it's the same variables as the last group. And then we have for meters again, 2D, 2 from there, minus 3E, and plus F plus 1 equals 0. And then for our time, you get minus D, 0 for E and 0 for F, and for our non-core group, you get minus 1 equals 0. So you get D equals minus 1 again, and similar to that setup, and your F group, using the same method we did over there, equals 1. You have your pi 2 group equaling your constant group velocity, or non-core group velocity, times your length dimension for F, and in the bottom for D, for -1 for D, you have your mass diffusivity constant, which is also known as the Peclet number. For our last pi group, we're going to do the same thing as before, same groups, and assign their coefficients. So meters squared per second again to G, density kilograms per meters cubed. For H, move back here, look at it later, and for meters for the length group, and then our last variable is our viscosity, which is kilograms per meter second, which is raised to the first power. Let you look at that real quick, and then I'm going to get to writing the same process of this. I just might block it out a little bit. So we have kilograms meters seconds. Again, we have to look at G. We have 0 for kilograms. I'll leave that 0 for G. Leave that blank for now. For H, we have 1, and for I we have 0, and for our viscosity we have 1. So +1 equals 0. So that'll tell us H equals -1. For meters, we have 2 for G. We have -3 for H, plus I -1 equals 0. Come back to that. When we have our last equation, we have -G, and then for seconds, and then H is 0 and I is 0, and then we have -1 equals 0. So G equals, add 1, -1. Knowing that H is -1 and G is -1, plug that into our meters equation. So we get -2, and then H is +3 plus I -1 equals 0, or that ends up being I equals, and 1, 2, I equals 0. So using that, we have our pi3 group equaling G is our mass diffusivity constant, equaling -1, and that's going to be on the bottom. And our H is -1, which is our density on the bottom. And then on the top, we have our non-core group of viscosity, which is also same thing as our, called a Schmidt number. Now for this problem, we need the Sherwood number, or the Sherwood dimensionless group, which we have for pi1, the Schmidt dimensionless group, which is pi3, but we also need the Reynolds dimensionless group. And to get that, you're going to use your pi2 and pi3. So you'll go pi2 divided by pi3. You get, which equals the Reynolds. You get that to be equal to velocity times our length group times our mass diffusivity And then so divide by pi 3, so we'll just flip it. Mass diffusivity times density divided by viscosity. Cross out your mass, diffusivity constants, give you Reynolds being velocity times length dimension divided by the viscosity. That should be it for the dimensional analysis. We'll leave the board up for a second. One last thing, the Reynolds number, forgot to write in the density, so it's actually velocity times our length dimension times density divided by viscosity.